So we've been talking about differential equations, and again, just to recap, the idea is that if we've got some equation that's talking about what the derivative is doing, maybe the derivative is 3x times y, or maybe the second derivative plus 2 times the first derivative is y plus x, or what have you. All right, so we have some sort of equation that is relating some information not only about the function itself, but about its derivatives. So we've been talking about this idea. One way to think about these is to think about some sort of slope field. We're going to now talk about an algebraic way of actually calculating the function in question. So first off, we're going to limit ourselves to first order differential equations. So again, first order means we're only working with derivatives, or we're only working with first derivatives. Anything that has a second derivative is going to be a second order differential equation. And we're going to deal with these later, right? So we're ignoring this, and we're focusing on first order differential equations. Just as a reminder, this doesn't have anything to do with any exponents. So maybe that's squared, maybe this is squared. That's totally a fine thing for there to be. The point is that we only have first derivatives. Okay, and when we limit ourselves to this, we typically write it in the form like y prime equals something. It just helps us keep things a little bit cleaner. I also wanted to remind everybody that there's a bunch of different notational ways of doing this. We can say y prime equals something. We can also say dy dx equals something. And either way we do it, sort of has pros and cons, but these two things we'll use interchangeably. Okay, so the idea is we want to find that function, that y equals something function, or I keep saying function, not necessarily a function, that makes these equations hold. And the way that we're going to do it is by separation of variables. So this doesn't work for everything. This only works for first order linear differential equations that are separable. So like a lot of conditions there. But this is just an approach that we can take. So when we write something dy dx, officially we're saying it's the derivative of the function y where your variable is x. But if you remember way back to when we first learned this idea, this dy means a small change in y divided by a small change in x. And so we're actually dividing something here. And so this isn't just notation. So what we're going to do is definitely something that usually you're not allowed to do, and we're going to break up this fraction. So the general idea is that we want to get all of the y stuff on one side and all of the x stuff on the other side, right? I'm actually going to work with a different function, one that's just a little bit easier to work with here, at least to start. So our differential equation is going to be negative x over y. Right? So this is some differential equation. We want to know, what do the functions look like that make this work? And like I was saying, we're going to move all the y stuff to one side, all the x stuff to the other side. So if we do that, if we multiply this dx across and multiply the y across, we get that y dy equals negative x dx. Right. And now we've got an equation with these d's, which strictly speaking isn't something that we're usually allowed to do. But we're setting this up to do something else that we're not allowed to do, which is integrate both sides. So there's a lot of sort of hand wavy, like, hey, we're allowed to do this. And there are rigorous ways of showing that this works. But the general idea is that because this dy dx is made up of a small change in the top over a small change in the bottom, we can multiply that small change over and then add a bunch of things up. In practice, it just means, hey, we can solve this algebraically. Right. So now we have this equation, which is something that we can actually get our hands on. So we're looking for functions, we're looking for y equals things. This is going to tell us what those are. So if we integrate both sides, the integral of y dy is y squared over 2. The integral of negative x dx is negative x squared over 2. And there's one really important piece that we forgot. And the main reason that we make such a big deal about it early on is that this is where we really need to remember the plus c. This plus c is going to give us, so when we say that there are infinitely many solutions to this, this plus c gives us that leeway. Because c is any constant, and this other is any constant, we can actually end up just combining these and just say, all right, well, this is some constant plus a constant. It's just a constant. You don't need to do c plus c or c minus c or anything like that. The point is that these two things are separate constants. We're combining them. It's just some single constant. Anyway, so this gives us our equation. So what we have now is y squared over 2 equals negative x squared over 2 plus some constant. We can multiply through by 2. And I'm going to go and move this part over. Y squared plus x squared equals some constant. And you might say, oh, it should be 2c. Again, c just means any number. 2 times any number is still any number. We can just call it c. Anyway, so this gives us our equation. So you might recognize this particular form if we write it another way, y squared plus x squared equals r squared. You may remember that this is the equation for a circle. And all the different c's are going to give us different radiuses of the circles. So the types of equations that make this work are equations centered at 0 are circles centered at 0 with various radiuses. All right, so I want to toggle over to our handy Desmos plot. So here we have the Desmos slope field generator that we saw in the last video, and I've put in our differential equation. We're looking for dy dx equals negative x over y. And we're going to see that what we have is this slope field where we can actually see that the solutions to this, if we were to sort of go with the flow for these equations, we would have circles. Oh, that's bad. But we would have circles like this. And the different flows that we have are the circles of different radiuses. Oh. You get the point. There we go.